email addresses on this slide, we'll be happy to send out the recording from last week that Nitij did. So MCAT 101, we have a mission to make MCAT prep fun and free. So for my part, these sessions are free. For the fun part, at least I hope that you guys find it fun and enjoyable. If you're not on the listserv or the newsletters, type your email address into the chat. And then when I review the chat logs after the session, I'll go ahead and add you to the newsserv, the listserv. Let's see, any other questions? Will these recordings be available after the session as well? Yes, you can email me or MCAT 101 questions, and we will send you the recording for this session. Right, so not everybody here, wait, I'm omitting somebody, give me one moment. Not everybody here was at the session last week, but I wanted to take a different approach and review also. So this will help all of us. So for acids and bases, we have three main definitions. We have the Arrhenius, the Bronsted, and the Lewis. In terms of the MCAT, the two definitions that are most important are Arrhenius and Bronsted, but you still need to know the Lewis definitions. So we're going to delve in a little bit deeper. Right. So I apologize in advance. I don't have a active ChemDraw subscription, so these chemical equations might not be the prettiest. Hopefully you can understand. These are examples of an Arrhenius acid and an Arrhenius base. So in the first example, let me see if I can get a laser pointer. Here we go. We have HBr in aqueous solution, breaks down into H plus aqueous and Br aqueous. So if we look at the definition, we're talking about an Arrhenius acid produces hydrogen ions in water. Likewise, an Arrhenius base, in this example, we have potassium hydroxide, breaks down into K plus and OH minus. So it produces hydroxide ions in water. So Nitij covered this in his session last week, but I wanted to point something out because I figured some people might have questions. When we're talking about hydrogen ions, we're talking about H plus in aqueous solution. In aqueous solution, H plus actually reacts with water to form the hydronium ion. You don't find H plus just floating around in water. You have H3O plus, but for purposes of the MCAT, we can use H3O plus or H plus to mean the same thing. Basically, we're talking about protons. To know where it's building from. Now, if we look at Bronsted-Lowry acids and bases, we have proton donors and acceptors. Now, this is why the definitions of acids and bases are a little bit confusing for people. So all Arrhenius acids and bases are Bronsted-Lowry acids and bases. So basically, Arrhenius is the narrowest definition, and Bronsted-Lowry is wider. So any Bronsted-Lowry acid or base is also an Arrhenius acid or base, but not vice versa. Right? So let's see. We have a generic acid, HA, A for acid, and H because we want to show the proton. A generic acid in aqueous solution could react with water, and then let's see what this forms. We form hydronium. Alternatively, you could also write H plus, but since I'm using water here, I want to put hydronium. We form hydronium and A minus. So here, HA, our generic acid, becomes A minus. So what changed from HA to A minus? We lost H plus. We lost a proton. So HA donated a proton, and by donating a proton, it became A minus. Whereas water, in this example, is the proton acceptor. Water is H2O, accepts a proton, and becomes H3O plus, or hydronium. Right. And if you have any questions, type it in the chat, and then whenever I notice it or I find a good stopping point, I'll go ahead and answer the question. All right. So normally when we're talking about conjugate acids and bases, we're talking about Bronsted-Lowry acids and bases. So in the previous example here, we had HA, and HA lost a proton, became A minus. So that is a conjugate acid-base pair, where HA is the conjugate, where HA is the acid, and on the product side, we would have the conjugate base to the acid. Whereas the other, we have two base pairs, conjugate acid-base pairs. The other one is between H2O and H3O plus. So H2O in this reaction acts as a base. If it acts as a base, once it gains the proton, it becomes an acid. So this is the conjugate acid to the H2O base. All right, so these are examples using a generic acid and base, but we can actually use our previous example of HBr to demonstrate a Bronsted-Lowry acid also. So if we look above here, we have HBr dissociates into H positive and Br minus in aqueous solution. I'm just rewriting this in a different form to show the water and the hydronium. So HBr reacts with water, and the water gains a proton, whereas HBr loses a proton and becomes Br minus. Right, and if you notice here, right here I have a double-sided arrow, and right here I have a single-sided arrow. The reason this is a single-sided arrow is because we will learn that HBr is a strong acid, and strong acids dissociate completely. That means that the reversible reaction is negligible. All right, now we're going to move on to Lewis acid and Lewis bases. So a Lewis acid and a Lewis base is, how do I put it? They're covered on the MCAT, but not as extensively as the Arrhenius acid and Bronsted-Lowry acids and bases. So in this example right here, we have ammonia reacting with boron trifluoride, and you see these two dots here, these are electrons, right? So we have a Lewis base, which in this case is ammonia, with a lone pair of electrons. The lone pair of electrons is used to form a bond with BF3, boron trifluoride, and this forms what's known as a coordination compound. When we study enzymes in biochemistry, we'll actually get into coordinate covalent bonds. For now, you just need to know that a Lewis acid is an electron pair acceptor. In this case, we're talking about ammonia. No, I'm sorry, I said that backwards. Ammonia is the Lewis base. It has the electron pair and it's donating it. And then boron trifluoride is the Lewis acid because it's accepting the electron pair to form this bond. We're later going to learn about coordination compounds. All right, so a Lewis acid is the most broad definition of acids, likewise for Lewis base. So all Lewis acids and bases are Bronsted-Lowry acids and bases and Arrhenius acids and bases. All Bronsted-Lowry acids and bases are also Arrhenius acids and bases, but the reverse is not always true. So for example, if we look at this right here, we have HBr reacting with ammonia, and we form their ions. So since ammonia is accepting a proton, it is a Bronsted-Lowry base. But if we look back at the definition for Arrhenius base, we're not producing hydroxide ions in water. So even though ammonia is acting as a Bronsted-Lowry base, it's not an Arrhenius base. But for any Arrhenius base, like for example, we have potassium hydroxide, it would also be a Bronsted-Lowry base. All right. So I mentioned earlier that HBr, hydrobromic acid, is a strong acid. So the easiest way to keep track of which is a strong acid and a weak acid is to look at how many strong acids there are and how many weak acids there are. There are a lot of weak acids, whereas with strong acids, we only have 7, some would say 6, that are important on the MCAT. The distinction between 7 and 6 is between chloric acid and perchloric acid. Some people only consider perchloric acid and they don't even include chloric acid, but it's not much of a difference. You have a difference of an oxygen, right? So let's think about strong acids. Strong acids have a large Ka and they dissociate completely in solution. So the reason I have a periodic table here is so that we can start looking into ways to remember these strong acids. So for me, I use a periodic table to remember these, and that's why I divided these into 2 groups. If we look at the top group right here, we have hydrochloric acid, hydrobromic acid, and hydroiodic acid. So let's see if I can get this pen working. So these are all in group 7. These are all halogens. So an acid that is formed with a halogen is called a haloacid, right? And this is just a generic haloacid. We have HX, where X is the halogen. All right. And then the acids on the bottom are all oxyacids. Now, if we look at the root here, oxy, that's because they all have oxygens. The proton, the H+, dissociates from the oxygen as opposed to a halide in the group down here, right? So now let's look into the haloacids, right? So we have hydrofluoric acid, which is actually a weak acid. It's at the top of this group right here. So we might ask, how come HCl, HBr, and HI, hydrochloric acid, hydrobromic acid, and hydroiodic acid are all strong acids, yet hydrofluoric acid is a weak acid? So to answer this question, can you repeat the organizations of the acids and bases? All Arrhenius acids, let me look. Let me go back a few slides. I'm gonna explain this. I apologize. On one of those run-throughs, I accidentally said it backwards. I corrected myself, but I did not mean to confuse everybody. So if right here, what I have written here is correct, if I can figure out how to circle it. Here we go. Right. So Lewis acids are the broadest. Lewis acids include Bronsted-Lowry acids and Arrhenius acids, but not the other way around. Does that make sense? Right? It's like the square and the rectangle. All squares are rectangles, but not all rectangles are squares. So all Arrhenius acids are also Bronsted-Lowry acids and also Lewis acids. All Bronsted-Lowry acids are also Lewis acids, but not vice versa. We can have Lewis acids that are not Bronsted-Lowry acids and are not Arrhenius acids. All right. All right, we were talking about why hydrofluoric acid is a weak acid while the rest of the haloacids are strong acids. This has to do with the size of the halide ion. So by halide ion, I'm talking about F minus, Cl minus, Br minus, and I minus. So as we know, elements that are towards the top of the periodic table are smaller than the ones at the bottom. So as we're going down, we have larger elements. So if we're looking at stability, F minus is much smaller than Cl minus. Because it's so small, it's not able to hold the negative charge as well as the Cl minus. It's not able to disperse the negative charge. So it prefers to keep the hydrogen as opposed to getting rid of the proton, which is what an acid is supposed to do. Acids, remember, are proton donors, but if the F minus is not stable, it's gonna prefer to stay as HF. So it's a much weaker acid than HCl, HBr, and HI. And actually, when we study periodic trends, we'll find that going down the series, we see increasing acid strength. So hydroiodic acid is the strongest acid out of the halo acids, and hydrofluoric acid is the weakest. All right. Actually, there's also a different way we can think about this. So if we're going down the group, halogen size increases. And what happens when the size of the halogen increases? It's going to make the bond length between the hydrogen and the halogen get bigger also. So if you have a longer bond length, you're going to have a weaker bond, right? So the weakest bond is between H and I. And if you have a weaker bond between H and I, you can more easily get rid of that proton. The more easily you can get rid of the proton, the more acidic you are. Because remember, an acid is a proton donor. So you want to be able to easily get rid of the proton. All right. I generally just use the periodic table, but I looked online and I found this mnemonic that I thought might be helpful for some people. This mnemonic is, so I brought no clean clothes. Sorry, which halogen is easiest to get rid of protons? Yes, I'm gonna go back to the slide, the last slide previously real quick. So hydroiodic acid, remember iodine is further down on the periodic table. So that means the size of the halide ion, I minus, is going to be larger than F minus. So since the size of the halide ion is bigger, it more easily gets rid of the proton, right? And if you're more easily able to get rid of the proton, then you're a stronger acid. Does that answer your question, or do I need to rephrase it? Could you also repeat the pKa of the stronger acids versus the weaker acids? All right. I don't have a slide for this, but I'm gonna give it a go at explaining. And if it doesn't make sense, let me know in the chat, and then I'll try to explain it a different way. So with acids, yes, what you're saying is correct. Strong acids have a larger Ka, and a Ka is the acid dissociation constant. It means a large Ka means you can dissociate more easily. Actually, let's use this other slide. I'm gonna go back a few slides. We're talking about dissociation, right? So if we're talking about whether an acid is strong or weak, a strong acid, such as HBr, dissociates completely. That means all of the HBr turns to H plus and Br minus. So the Ka is a number, it's the equilibrium constant between, for this reaction. So since HBr dissociates completely, it's a strong acid, that would mean its equilibrium constant is very large, because whenever we're forming equilibrium constants, it's the concentration of the products over the reactants. So you have very large products because it dissociates completely, and very minimal number of HBr because it's a strong acid and dissociates completely. When you have a large number and you divide by a small number, you get a larger number. right? And then pKa, if you have P before anything, when you're talking about sciences, it means the negative log of something. When you take the negative log of a number, the orientation of whether large or small actually flips. So if you have a large Ka, you have a small pKa. If you have a small Ka, you have a large pKa. That's correct. I'm just thinking to make sure I didn't phrase that wrong. I'll explain a little bit more about pKa in another slide. All right. So I was going over this mnemonic. Honestly, I memorize it using the periodic table. It's easier for me, myself, to just remember it based on the periodic table, so I have one less thing to remember. But if this helps you, go for it. So we have SO for the sulfuric or sulfate once it breaks down. We have I for the hydroiodic acid, Br for bromine, NO for nitric, clean for Cl, and then close for chloric acid or perchloric acid. I found another mnemonic, and if I was going to use a mnemonic, I think I prefer this one. So this is I bring cans of Coca-Cola, so no. The reason I like this one better is because the arrangement of these acids actually goes from strongest to weakest. Okay, I thought I labeled that backwards for a second. I probably should have just labeled the top and the bottom to make it simpler. Basically, this is the strongest acid and this is the weakest acid. What's the trick using the periodic table? Let's go back. So honestly, for acids, I just look at the halogens, and I know that the 3 lowest halo acids are the strongest, are 3 of the strongest acids, 3 of the strong acids that we have memorized. And then you kind of have just have to remember that hydrofluoric acid, because its halide ion is smaller than the others, it actually prefers to stay as HF, and it's a weaker acid than the other 3. And as for the other strong acids, they're all oxyacids. So oxyacids have the proton dissociating from the oxygen as opposed to a halide. There's only 7 or 8, depending on if you're counting this as 1 or 2. Strong acids. So you can memorize it without the mnemonic, with the mnemonic, with the periodic table, whichever way makes sense to you. All right, and then with the bases. The bases, I arranged them this way so that you can look at the 2 different groups, right? So these are the strong bases that you'll see most often. There's also another group called super bases, but the super bases, when you're talking in general chemistry, you're not going to get to. In organic chemistry, the organic chemistry portion, you're going to get into stuff like sodium hydrides, which is a super base, and that's going to be used to synthesize some things. But for now, these are the strong bases you would need to know for the general chemistry portion. So if we look at the list, we have lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide, and you're not really going to find this in nature quite often. I would be surprised if you got a standalone question with this. If you did, it would probably be in a passage, and they would probably explain it to you anyways. So basically, if you have a hydroxide of group 1, also known as alkali, the alkali elements, alkali metals, these are strong bases. And then if we look at the bottom 3, let me circle these. We have calcium hydroxide, strontium hydroxide, and barium hydroxide. These are alkaline earth metals. So these 3 are strong bases, whereas beryllium and magnesium are weak bases, right? So when on the MCAT, you are given a periodic table. Honestly, if you look at the periodic table and you remember that the group 1 alkali metals and the bottom portion of the alkaline earth metals, the hydroxides of these are strong bases, you'll be fine. You don't have to remember them by name necessarily, but once you work through enough problems, you'll see sodium hydroxide so many times that you probably won't be able to forget that it's a strong base, right? Other strong bases you might see that are not hydroxides would be hydrides, amides, alkoxides, or carbides. Honestly, don't worry about them right now. When you start reviewing organic chemistry, maybe even one of my sessions, we'll talk more about those. Right? So here's an example of finding a pH question. So we're looking at what is the pH of 0.002 molar HCl. So in order to solve this, we would actually have to know that HCl is a strong acid, so that we know that it dissociates completely. So HCl dissociates into H+. And earlier I was talking about pH. So since we know it dissociates completely into H+, we know that we also have 0.0020 molar of H+. If this was a weak acid, we wouldn't be able to evaluate this question without more information, such as the pKa, because we wouldn't know how much of it dissociates. Some of it might stay in HCl form, but since it's a strong acid, it dissociates completely, and we know that the concentration of HCl is equivalent to the concentration of H+ or hydronium ion H3O+. So remember that pH, P of anything means negative log. So the negative log of the concentration of H+ is how we're going to find the pH. So I rewrote 0.0020 in scientific notation. We're going to break this down further in the next few slides to see why I did this. But for now, we can break this down into the negative log of 2 plus the log of 10 to the minus 3. And if we evaluate this, I'm going to explain how we evaluate this without a calculator in a future slide. But the second term here ends up being 3. And then log 2 is 0.3. So we know that 3 minus 0.3 is 2.7, which would be the answer to this question. This is just to show you why logarithms are important when we're dealing with acids and bases. Right? So with logarithms, I'm switching to my laser pointer real quick. Here we go. This is called the exponential form. We have 10 to the x equals 1,000. Right? If we wanted to convert this to a logarithmic form, we would do log of 1,000 equals x. Basically, logarithm form says if we take the log of both sides, I'm trying not to confuse everybody. Give me one moment. Okay, here's how we're going to do it. So you can have different bases for logs, but on the MCAT, we're dealing with log base 10. So we learned that log base 10 kind of cancels the base here. So basically 10 to the x, if we take the log base 10, we get rid of the 10 and all we're left with is x. So this left side of the equation actually becomes the right side. So since if we do one operator to one side of the equation, we also have to do the same operator to the other side. So all I did from this step to this step was I took the log of both sides, but then I also switched the sides, and that's why I was worried about confusing everybody. So basically, log of 10 to the x just becomes x, and log of 1,000 is what we're left with. Right? So then, if we rewrite 1,000 to scientific notation, that would be log of 10 to the third equals x. And that is equivalent to 3. So here we can learn a trick from this. Since we're dealing with log base 10, log of 10 to the x is always equal to x. For example, if we had log of 10 to the 5th, x would be 5 because it's 10 to the 5. The answer would be 5. Log of 10 to the 6 would be 6, and so on and so forth, right? So here are just a few more examples. Log of 100 is equal to 2. Another way you could do this, once you get used to it, is you can just look at the number of zeros. So I mean, you know that this has 2 zeros, so that would be 10 to the 2nd power. And then if we keep dividing by 10, we can also find out that log of 10 is the same thing as log of 10 to the 1. Let's see. So this one might be confusing to some people. Log of 1. So anything to the 0th power is equal to 1. So we can use this to find out that log of 1 is equal to 0. If this doesn't make sense to you, the 10 to the 0 thing, just memorize that log of 1 is equal to 0, right? And basically every time you move the decimal, you change the exponent by 1. So up here we had 1,000, log of 1,000. So that is 10 to the 3rd, right? But if we had moved the decimal place over 1, then we get 10 to the 2, and the log is decreased by 1 every time we move the decimal over to the left one. So with 10, if we move the decimal over 1, it becomes 1. So it's 0. So by using this, we could also find out that log of 0.1 is -1. And that might be easier for some people than doing 10 to the -1. But an alternative way to do 10 to the -1 is to remember that when you have a negative exponent, it's the same thing as 1 divided by the positive exponent. So this would be equivalent to 1 over 10 to the 1st power. 10 to the 1st power is 10. 1 over 10 is equivalent to 0.1. So log of 0.1 is equal to -1. So all of these examples are using log base 10. So what do we do when our number is not a simple power of 10? We have right here log of 3 times 10 to the 5th. We can evaluate very easily log of 10 to the 5th because we remember that log of 10 to the x is equal to x. So log of 10 to the 5th is just 5. But how do I figure out what log of 3 is? Right? So this is the previous example we had. Right here are the 3 logarithm laws. Let's see, where would you have learned this? I think between algebra and geometry is usually when most people start learning logarithms. So this first law here just tells us that if we have the product of something, we have log of x times y, there are parentheses here basically. You don't have to put the parentheses, but if they help you, you can put them. So this is log of something that is x times y. You can rewrite that as log of x plus log of y. So if you have the log of something that's multiplied together, you can break them apart to make them log of one of the parts that are being multiplied plus log of the other part. In the previous 2 slides, I have a private question. Give me one moment. In the previous 2 slides, can we still use? All right. Somebody's asking me if we can use the pH equation to find the concentration of HCl. Actually, yes, we can. I just want to make a note here. The P of anything is the negative log of that. So for pH, we would actually take the negative log of the hydrogen ion concentration. What equation did I have here? Right. So right here, I took the negative log of this entire concentration. If you type this into a calculator, negative log, make sure all of this is in parentheses, you would end up getting 2.7. The reason that we're discussing doing logarithms without a calculator is because on the MCAT, we don't have a calculator. As for the autoionization of water, which is the other part of the question that somebody asked, In this set of slides, I haven't discussed the autoionization of water. I'm happy to discuss that question via email or in a future session. Do me a favor and send me an email if you need the question for that, or if you want me to cover that in a future session. I plan to do one more session on acids and bases, just because this session is a little bit overloaded, so we won't have time to do many practice questions. But if we get enough interest in another session, I'll cover the autoionization of water, and I'll also cover weak acids and bases more in depth. All right, so with this first law here, if we have the log of a product, we can divide it in, we can break it down into the log of the individual constituents, right? Likewise, with division, if we have log of x divided by y, we can break this down further with subtraction. We can do log of x minus log of y, right? So if we have log of 1/2, for example, we could do log of 1 minus log of 2. For this one in particular, if we memorize log of 1 is equal to 0, we know that this is just equivalent to negative log of 2. Or if we remember that 1 is equal to 10 to the 0, log of 10 to the 0 would be 0, right? But we're going to evaluate this one after we go through a little bit more with logs. And then this last law here has to do with exponents. If we have log of x to the n, we can pull out this exponent and make it into a multiplication question, basically. So if we have log of 3 to the 5th power, we can pull out the 5 from the exponent and just do log of 3 multiplied by 5. Right? So this is how I think of logarithms. Hopefully it helps with you guys too. So I memorized 2 logarithm values. I memorized the log of 2 and the log of 3. So the log of 2 is 0.3 and the log of 3 is 0.48. For most questions on the MCAT, you could honestly get away with memorizing log of 3 as equal to 0.05. It'll make your calculations simpler. I had already memorized it as 0.48, so I continue to use this value. But you won't get the majority of questions wrong if you use 0.5 unless the answer choices are very, very close together, right? So here for log of 4, we can go back and we can think about how we can make 4 using log of 2, right? So log of 4 could also be log of 2 times 2. So we could find log of 2 and multiply by 2, or we can think of the 4 as 2 to the 2nd power, which actually leads us to the same equation. If since we know that we can pull out this exponent because of the third law that we learned, we pull out the exponent in front of the log. So now it just becomes 2 times log of 2. And since we know log of 2 is 0.3, log of 4 is 0.6. So at this point, I've used logarithms so much that I basically memorized log of 4 as being 0.6. But if we had gone back to before I memorized it, all I had to do was memorize log of 2 and log of 3, and I can find out the majority of the rest of these logs. So I could find out that log of 4 is 0.6 just by remembering what log of 2 is. And I can't figure out how to advance my slide because the laser pointer is stuck. Here we go. Right, now we're going to look at log of 5. So how can we figure out what log of 5 is using the log values that we know? So we know log of 2, 3, and 4. The easiest one to actually use would be to think of 5 as 10 divided by 2, right? So we know that 5 is equivalent to 10 divided by 2. And since we know we can split up this division into two logarithm components, with the second one being subtracted, we know this is equivalent to log of 10 minus log of 2, right? Log of 10 is equal to 1, and log of 2 is 0.3. So we can evaluate this and find out that log of 5 is equal to 0.7. What can we do for 6, right? So here we use division between 10 and 2. And since 6, if we were going to divide, we would use 12 divided by 2. We don't know the log of 12. So instead of using division, we could actually use multiplication for this one. We know the log of 2. We know the log of 3. So how about we evaluate the log of 2 plus the log of 3, right? So we have log of 6 is equal to log of 3 times 2. And that's true because 3 times 2 is 6. We can break this down into log of 3 plus log of 2, right? This becomes 0.3 plus 0.48. So we can evaluate and find out that log of 6 is 0.78. Again, if you haven't already memorized it and this is confusing to you, you can use 0.5 for 3. In that case, we would get 0.3 plus 0.5, and then log of 6 would evaluate to be approximately 0.8. And for purposes of the MCAT, that approximation will get you the majority of the logarithm questions correct, right? So here I skipped log of 7 because 7 is a little bit more complicated. We can't form 7 easily by multiplying or dividing any of the other logs. So if we do log of 8, we know that log of 8 is equivalent to log of 2 times 2 times 2, or 2 to the third power. Most people may not be able to break down 2 to the third very easily, but you could have figured this out by seeing that 8 is 4 times 2, and 4 is 2 times 2, so 2 to the third power. Or you could also use log of 4 and log of 2 to figure this out. In this example, I pulled out the 3 exponent to the front. I know that log of 2 is 0.3, so I evaluate this to be 0.9. So looking at this right here, I'm going down an increasing order of logs, right? So we know log of 6 is 0.78, or about 0.8 if we had used the 0.5 approximation here. Log of 6 is about 0.8. Log of 8 is about 0.9. So log of 7 has to be in between these two, right? So if you want it to be more exact, you could use 0.845. Again, for the purposes of the MCAT, you could just round this. So if we round this, we get 0.8. This is 0.9. In between 0.8 and 0.9 would be 0.85. So if you use 0.85 for log of 7, you would be perfectly fine. And then let's think about how we would do log of 9. So log of 9, we have 1 times 9, or 3 times 3. We don't know log of 9, so using 1 times 9 would be useless. So we have log of 3 times 3, right? So we can pull out the squared if we're using exponents to make it 2 times log 3, or we can do log of 3 times 3, and that would just be log of 3 plus log of 3, which is the same thing as 2 times log of 3, right? And if you use the approximation here of 0.5, this would end up being 1. So actually, if we approximate the highest values, this is 0.8, 0.85, 0.9, and 1. It's not the most complicated ones to remember. It's probably easiest though, just to memorize 2 and 3, and then know how to quickly calculate these if you need them. You can also calculate fractions using division, but if you have a proper fraction, proper meaning the numerator is smaller than the denominator, we know that it's going to be a smaller value because log of 2 is 0.3, log of 1 is 0. So log of a fraction has to be less than 0 since log of 1 is 0. All right. So we're revisiting our examples with the logarithm laws. So how can we solve our first example? We broke this down into log of 3 plus log of 10 to the fifth, right? So we learned in this third law actually that we could pull out the 5 to the front here. But for this case, there's no point because we know log of 10 to the anything is just that anything. So we can evaluate the second term very easily. With log of 3, we simply just have to memorize this. So you can use 0.48 or 0.5. But now that we know that log of 3 is about 0.5 and we know this is 5, we can evaluate this. All right. So you can also use the approximation here. 0.5 plus 5 is equal to 5.5. And once you have log of 3 memorized, this one is very, very quick, and you wouldn't even have to write it out. You could do it in your head, which is advantageous for the MCAT. Right? So for our second example, we know that the log of a fraction is the difference between the log of the numerator and the log of the denominator. Right? Log of 1 is 0, and log of 2, remember, is 0.3, right? So I said previously, the log of any proper fraction is negative. Since log of 1 is always 0, no matter what number we put on the bottom, we're going to end up subtracting that number, right? So the log of a proper fraction is always negative. Right. For the last one, we can pull out the 5. We know that log of 3 is equal to 0.48. If we approximate this, that would be 0.5. 0.5 times 5 would be 2.5. All right. So let's revisit this example. So now that we know what log of 2 is, and we know something about the logarithm laws, this one is actually a fairly easy question. We know that 0.002, we moved the decimal over 3 times, so we can rewrite that in scientific notation as 2 times 10 to the negative 3. Since these are being multiplied, I can split up these terms into the sum of log of 2 plus log of 10 to the minus 3, right? Right here, I'm just distributing the negative sign. The reason I'm distributing it is because we have a negative exponent, and as we'll see, if we lose this exponent, it's gonna mess us up. So I went ahead and distributed it. We have minus log of 2 minus, so log of 10 to the anything is just that anything, right? 10 to the x, log of 10 to the x is equal to x. Since x is negative 3, we put negative 3 here, but we had the negative sign here already. So these two negative signs actually cancel, and this term just becomes 3 minus log of 2. And since we memorize, or we will memorize, that log of 2 is equal to 0.3. 3 minus 0.3 is 2.7. All right. Okay, this is a similar question. So now, instead of looking at something with HCl, we're changing the concentration of HCl. Instead of looking at 0.002 molar, we're now looking at 0.006 molar. So with 0.006 molar, these steps are mainly the same. So what I want to focus on here is what's actually different. So instead of having a 2 here, we have a 6 here, right? So everywhere we had a 2, we have a 6. So we'll notice that the second part of the term, once we write into scientific notation, the 10 minus 3, it doesn't change. Since these are both have the same number of zeros, or the same number of zeros before the this unit. So there's 2 zeros before the 6 and 2 zeros before the 2. They both end up, once we write them into scientific notation, being 10 to the minus 3. So there's a shortcut here that you can learn. Basically, if you rewrite anything in scientific notation, and you take the negative log of that, you can easily find out by counting how many times you move the decimal place and finding out what the first term is. So for example, in this equation, if I wanted to write this in scientific notation, I would move it over 3 times, right? So I know this first term is going to be 3, no matter what this number is. I can change this to a 7. If I change this to a 7, it would be 3 minus log of 7. If I change this to 8, it would be 3 minus log of 8. And once you notice this pattern, this makes it a lot easier when you're evaluating questions, because you can go ahead and look at this, and without writing all this out, you already know that this is going to be equivalent to 3 minus whatever the log of the whatever digits here, right? So we can do 3 minus log of 6. Now, how do we find log of 6? This is kind of looking back at what we reviewed earlier. So the log of 6 is, we can break this down using multiplication as the log of 2 times the log of 3. All right, here we go. So we have 3 minus log of 3 plus log of 2. And this is going to evaluate to being 0.48 minus 0.3. So log of 3 you can approximate to be 0.5. Log of 2 you can approximate to be 0.3. So 0.5 and 0.3 is equal to 0.8 right here. 3 minus 0.8 is 2.2. And all right. Does anybody have any questions? I'm taking a look at the time real quick. I timed that out almost perfectly. We have 2 minutes for the hour. I'm going to wait another minute here just in case anybody has a question. If not, I'll wrap up with my last 2 slides, and then we can continue this talk in another session. Well, of course, practice makes perfect with all these logarithms and all that. I want to go through some problems, but we're not going to, I had to plan for an hour, and in order to cover those topics, there was no way we were going to be able to do it with all the practice questions. So I had to split it up into 2 sessions. Any good practice for log problems you recommend? Honestly, you can look in, and you could probably go to Google, type in log practice, and you could do some log practice with that. But the easiest thing would be to find a MCAT textbook, an MCAT practice book, and look in the acid-base sections. And their questions involving pH all have to do with logarithms, because that's what we're going to be doing. So let's see. This is our GoFundMe. If you've been to any of our other sessions, you've heard from Sim or Nitij. We're doing this for free. And we have to cover our website, advertising, and other costs. So if you'd like to donate to our GoFundMe, again, this is not necessary, only if you want to, you can go to this link. And yes, this is the more important point. Please share with your MCAT study buddies, right? We want to be able to continue doing the service, and we want to have broad access to a large group of people. So having more people attend these sessions would be helpful for us. Right. So this is my email address again. For everybody who's already on the listserv, I will send out this presentation for you shortly after this presentation. And anybody who left their email address in the chat, I'll also add you to the listserv. Let's see, what am I saying here? Oh, I said this already, but basically I want to delve further into more examples using all of this, but we weren't going to have enough time. So if you're interested in another session dealing with more examples and going through logarithms, especially with weak acids and weak bases, send me an email. Let me know you're interested. And if we get enough interest, I'll do a follow-up session. For next week, right now I'm working on an amino acid session. So I plan on covering amino acids, but depending on the interest levels, I may switch the session. I'll wait a few days, and then when the newsletter comes out, we'll see whether I'm doing the amino acid session first, or if I end up doing another acid-base and logarithm session. If you have any other questions, you can email mcat101questions@gmail.com, or you can email my email address. And let's see, will there be organic chemistry sessions in the future? There are. So actually, the way we've structured these sessions so far, we had a Google form, and we basically asked people to fill out what they were interested in learning about. And I rearranged the number of answers that came in, and we basically just each selected the topics with the highest number of votes. We've had one session so far on biochemistry, dealing with catabolism and metabolism. Right now, my research was started out in field biology, and then I studied flavin-dependent enzymes. So actually, I'm more comfortable talking about biochemistry than general chemistry, but these are the basics. And since I wanted to teach amino acids, I had to do an acid-based lecture so that we would be able to come in understanding acids and bases for the enzyme lectures. Again, if you want to learn about a specific topic, you can reach out to the MCAT 101 questions and suggest that topic, or to my personal email. Actually, you know what? Go ahead and send an email to both email addresses. So send it to me so that I can know to plan for it. But since everybody on our team monitors this email address, send it here just to make sure I don't lose track of it also, right? For organic chemistry, if I recall off the list, the topics that most people had trouble with was SN1 and SN2, and also acid-base catalysis, which is another reason we had to cover acid and bases first, because you have to understand acids and bases before you can understand acid-base catalysis. What other topics? Amino acids are also in between organic chemistry and biochemistry. All right. So that's it for my presentation today. Let me know if you have any other questions. I'll hang on for a few more minutes just in case we get a few more questions. I know you mentioned that you haven't posted the videos yet. Yes, so we're considering posting the videos. We haven't decided how we're gonna do it yet. So we thought about doing a YouTube channel. But then we ran into, we know there's other resources out there such as Khan Academy. And Khan Academy actually has some really extensive videos, and they're good videos. I actually used their videos when I was studying for the MCAT. So originally they were planning on canceling their MCAT videos to focus more on K-12 education. But because of COVID, and probably because a lot of people sent emails, they're extending the date. So they're going to hang on, I believe, for another year before they get rid of all those videos. So in the future, those Khan Academy videos may not be available. For now, they're an excellent resource and you can use them. So we're considering uploading all of these to YouTube, but if a point that was brought up is the reason we started doing these sessions is because we wanted to do live sessions so we could answer the questions as they come in. So I mean, we can still do live sessions and upload it to YouTube, but we wouldn't be able to, we'd have to have somebody be around to answer the questions on the YouTube videos. So we're thinking about it. We'll let you know if we end up sending it to YouTube. For now, if you want a video of a specific session, just send us an email and we'll be happy to send you that video. Well, I mean, if we were going to do the YouTube videos, it wouldn't be instead of these sessions. So I'm answering somebody's point here. We would still do these sessions, but we were considering whether we should post these on YouTube or not. Another point of contention that some people are wondering about is the practice questions. So for me, I rewrite practice questions that I think of from my head. And honestly, like for instance, this session, we had HBr and HCl. No matter what textbook you open up, you're gonna get the same examples of strong acids. So I'm not plagiarizing, you're just, there's only 7 or 8 strong acids. If you write a question, you're gonna end up getting the same question. But we can't, for instance, use UWorld or Jack West In questions if we, because we'd get into trouble with copyright, and then that would put us into some really deep trouble if we posted it on YouTube. So depending on who the person leading the session is, they may be using questions that come from published materials. And if they did that, we wouldn't want to get in trouble with copyright. All right. Are there any books you recommend for using to begin MCAT prep? So it depends on the person. So I mentioned in Nitage's last session that I like Exam Crackers. Most people say that Exam Crackers doesn't go in depth enough. So with my background, I have a bachelor's and a master's in biochemistry. I conducted research for a long time. So I have the basics fairly well embedded in my head, embedded in my head. And I've taught general chemistry and I've TA'd before. So I know most of the concepts. I just needed a brief review and then to know which topics are going to be important to the MCAT as opposed to studying all of general chemistry. So if you have a really solid foundation, I would recommend Exam Crackers. If your foundation is not as strong, different people recommend different things. There's Kaplan, Princeton Review, and Berkeley Review. Out of these materials, I think the majority of the people would use Princeton or Kaplan because they're the most accessible. Berkeley Review in particular, they go very, very in-depth with their material. For me, because I love the sciences so much, I would probably enjoy the Berkeley Review materials. But they may go so far in depth for somebody who's not interested in knowing all the low yield topics. So if you're limited on time, definitely don't go to Berkeley Review. If you have time, maybe consider Berkeley Review. If you're a person who wants to know the nitty gritty, you want to get a perfect score, you're one of those ambitious people, or you're a conceptual learner. I'm a conceptual learner. I like concepts and you want to understand how it works, I would go with Berkeley Review. Otherwise, for the majority of people, go with Princeton Review or Kaplan. If you have a solid foundation, you just need a review. Exam Crackers is a good resource. Who do I email for this recording again? You can email this email address or me. If you're going to email me, it's my session. This is my session, so I'll email you back right away. But if you email me about somebody else's session, I'll still answer you. It just might not be right away because I'll have to go and look for their recording. So if for any session, you can email this email address and get a reply right away. If you email to me, I'll reply usually within 12 hours for my sessions and within 24 hours or whenever I can get their video if it's not my session. Right? Were there any other questions? According to your experience, which resource? Okay, I talked about that. Do you also do physics videos? I can do physics videos. Nitage actually already did one for, if I can remember the topic, drawing free body diagrams. So if you're interested in free body diagrams and you haven't seen that lecture, you can send an email to either one of these email addresses, and I'd be happy to send you the video or the slides or both to the free body diagrams. For physics in general, I'm considering doing a one on what's called dimensional analysis. This just means you're using units to solve the problem. If there are any other topics that you want me or Nitage or anybody else to get into, send us an email and let us know what topic you're having trouble with or what you want us to delve into. All right. I think I covered everybody's questions, but repeat yourself if I skipped you by accident. All right. Have a good night, everybody. Expect the slides in your email address within the next hour or so. I have to go and add everybody else to the listserv first, and then I'll send out an email to everybody who is on this session. All right, and if you have any other questions regarding this session, you can email me and I will answer back. right? I have to work also, so just know that it may take me up to 24 hours, but the majority of the time I answer within 12 hours. All right, looks like we're done with questions. Have a good night, everybody. Hope you enjoyed the session. Hope I didn't bore anybody. Okay. And now I'm trying to figure out how to end the session. Here we go. All right, good night, everybody.